Have you ever rubbed a balloon on your hair and then watched it just stick to the wall? Like magic.
Yeah, it just hangs there, defying gravity.
Exactly. Or, seeing a huge lightning bolt flash across the sky. It's this raw power, seemingly from nowhere.
Mm-hmm. These invisible forces are all around us.
They really are. And that's what we're diving into today. Welcome to the deep dive. We take sources, unpack them, and, well, try to find the key insights for you.
Your shortcut to understanding some complex stuff.
Precisely. And today, it's something really fundamental. Electric fields and the basics of how electricity actually exerts force.
We're pulling back the curtain a bit on that unseen electrical world.
And making it accessible, hopefully, even if you're totally new to this.
Absolutely. And our guide for this is John Byung-Chul's book, Authentic Beginner's Walk Through Electricity.
Which sounds perfect for this.
It really is. It's designed to break down these, well, sometimes abstract-seeming ideas into simple, relatable terms. Great for demystifying things.
Okay, so our mission today, get you a clear picture of what an electric field is, how things get charged up, that's electrification, and crucially, how these charged things interact, push or pull.
The fundamental rules of the game, basically.
Exactly. Let's get into it. Let's unpack this.
Right.
So electric fields. To sort of get our heads around this, let's use an analogy. Think about maybe a school playground.
Okay, yeah, a playground.
What's it for? It's a space, right? For running, games, maybe big school events.
Yeah.
It's a zone where activity happens.
Mhm.
It enables the interaction. The space itself isn't doing the playing, but it's where the playing occurs.
Right. And electricity, surprisingly, has a similar idea, this electric field.
It does. It's fascinating. The electric field, or AML, is that specific area around an electrically charged object, what we just call a charge, or AM, where its force can actually be felt.
So it's the zone of influence?
Exactly. It's the space where electricity, you could say, plays or exerts its force on other charges that enter it. Okay, but we can't see these fields, can we? That's the tricky part.
No, they're invisible. But the source gives us a really helpful way to visualize them using lines, electric field lines.
Oh, right. Like drawing wind currents, even though you can't see the air moving.
Precisely. These lines aren't physical ropes or anything, but they map out the invisible force. They show the direction a tiny positive test charge would move if you placed it in that field.
So they point away from positive charges and towards negative ones.
That's the convention, yes. Radiating out from positive, converging in on negative, it gives you a picture of the force's direction everywhere in that space.
Okay, that helps visualize it. But what about strength? How strong is the force in different spots?
Great question, and very important. The visualization isn't just for looks. It tells us about the intensity. The source explains that the density of these lines, how closely packed they are, shows the field strength.
So lots of lines bunched together means a strong force.
Exactly. Where the lines are dense, or sealed as the source puts it, the electric force is strong. Think of more force vectors in a small area.
And where they're spread out, or...
The force is weaker. Sparse lines, weaker force. This concept, electric field line density, or Akeshaw, is super important in engineering.
How so?
Well, it helps predict things, like where electrical stress is highest in insulation, or how to shield sensitive electronics. You know where the strong interactions are happening.
Gotcha. Okay, so we have this invisible field, this space where forces act. But how do things get charged to create these fields in the first place? Become positive or negative?
Yes. The origin story. This is where it gets really interesting. It often happens through very mundane, everyday actions.
Like?
Well, think about combing your hair, especially if it's dry.
Oh, yeah. Static city. Hair sticking to the comb, maybe standing on end a bit.
Exactly. Or pulling a wool sweater over your head in winter. You hear that crackling.
Yeah. Little sparks sometimes. So what's actually going on there? Is electricity just appearing out of thin air?
It might feel like it.
Yeah.
But no, our source is clear. Before you started combing, both the comb and your hair were electrically neutral.
Meaning balanced. Equal positive and negative charges.
Precisely. A calm state, charge equilibrium, or red jock. No net charge on either object.
So what breaks that balance? What happens during the combing?
Friction. The rubbing action. It causes tiny particles, electrons, to actually move from one object to the other. This transfer is everything.
Electrons jump ship.
Basically, yes. For example, electrons might move from the comb onto your hair. The comb, having lost negatively charged electrons, now has more positive charges left behind. so it becomes positively charged.
Okay, makes sense. It's left with a net positive charge.
Right. And your hair, having gained those extra electrons, now has an excess of negative charge, so it becomes negatively charged.
Ah, so it's a trade. One loses, becomes positive. One gains, becomes negative.
Exactly. And this whole process where neutral objects become charged because of some external influence like friction, that's called electrification,
Hmm.
where the equilibrium is broken and boom, you had charged objects.
And those charged objects now create their own electric fields.
They do. And they can exert forces. This isn't just about annoying static cling. It's the fundamental principle behind forcing electrons to move in a circuit, too.
Right. So, okay, now we've charged things. A positive comb, negative hair. What happens next? The source says this made electricity now has power, force.
It absolutely does. Once that balance is upset, forces come into play. And the way these forces work is actually very similar to something else we're all familiar with.
Which is,
Magnets.
okay. Like poles repel, opposite poles attract.
Exactly that principle.
Yeah.
Charged objects interact in two main ways, just like magnetic poles. It depends on whether their charges are the same or different.
So let's break that down. What if the charges are the same, like two positively charged objects?
Yep.
Or two negative ones?
They push each other away. Our source calls this repulsive force, or
Like trying to force two north poles of magnets together? They just resist?
precisely, same charges repel. Doesn't matter if it's positive, positive, or negative, negative. They exert a force pushing each other apart.
Okay, repulsion. And the opposite. Different charges, like our positive comb and negative hair.
They pull towards each other. This is attractive force or a
Like a
covalent.
north pole and a south pole snapping together.
Exactly. Opposite charges attract. That's why your negatively charged hair is drawn towards and sticks to the positively charged comb. It's that fundamental pull.
And the source emphasizes if things are neutral, none of this happens.
Correct. No net charge, no electric field to speak of, no force between them. The magic, the force, only appears once electrification happens and you have that imbalance of charge.
Attraction and repulsion. It seems simple, but it governs so much.
It really does. This interaction, which we can actually quantify with something called Coulomb's law, isn't just static electricity. It's the basis for how atoms hold together, how molecules form. The very structure of matter relies on these forces between positive nuclei and negative electrons.
Wow. Okay, so let's recap quickly. We started with the electric field, this invisible playground where forces act.
Mapped out by those conceptual field lines showing strength and direction.
Then we saw how things get charged through electrification, basically. Electrons moving due to friction or other means, like the comb and hair example.
Breaking that neutral balance, creating positive and negative charges.
And finally, these charged objects interact with forces attraction for opposites, repulsion for same charges.
A lot like magnets, but operating at that fundamental charge level.
So why is understanding all this basic stuff so important for, our listeners?
Well, that's a key question, isn't it? Because these principles, that electricity has this influence in space, that charge imbalances can be created easily, and that they follow these push-pull rules, this is the absolute foundation.
The bedrock for everything else electrical.
Pretty much. It helps you understand how the devices you use every single day actually work, from tiny phone chips to huge power grids. It's the unseen architecture.
Without grasping this, it's hard to appreciate the tech around us.
Exactly. Or even natural phenomena. That static shock is a small version of the same principles that drive a massive lightning bolt. It all starts with separated charges in the fields and forces they create. It's the first step to understanding the energy shaping our modern world.
That's a great way to put it. So maybe next time you feel that little zap from a doorknob or see lightning.
You'll see it a bit differently.
Yeah. Maybe think about those tiny charges, separated by simple friction, creating powerful forces and invisible fields all around us. It makes you wonder, doesn't it? What other everyday things are happening because of these basic electrical principles working away unseen?
It's a whole world built on these interactions. Plenty more to explore.